The spinning hoop of doom. Okay. Hello, I'm David. It's semester 2 in 2022, and this is a revision seminar for Maths 1M. I've already done a bit on study skills, and this bit is going to be about visualising stuff. So let's see how we go. Okay. So the first thing that you've mentioned is planes. So right. So one of the things I said earlier is that as mammals you have bodies, like as animals you have bodies, and your brain uses your body to remember and learn things. So sometimes the trouble you have with visualizing things is that you haven't walked it. So here we are in the Flenchy Lecture Theatre. You say you can't visualize a plane?
I find it very difficult to read these days.
Yep.
So you try and figure it out.
Yep. So you live in 3D space. You have walked on planes your entire life. This is a plane. And that's what it feels like to be on a plane. You're going to walk around, here it is. I love it. Here is the plane. But so is this. This is also a plane. Okay? And when I look at where this plane meets this plane, it's here. That's a line. So one of the ways to visualize things is to walk them, to imagine being there yourself. Imagine you are much smaller than the thing that you are visualizing. Here I am, and I'm small enough to see that this plane goes on forever in all these directions. Look how wide it is. But just to be even more, most of the planes that we experience in everyday life are horizontal or vertical. And some planes are not. That's what these are for. These are in the Maths Learning Centre. Just take me a moment. That plane is neither horizontal nor vertical. It is diagonal. If you've ever made tents, you've seen planes that aren't horizontal and vertical. Now, it's not exactly straight, because the planes are straight, but that's an idea of what a plane is doing when it's diagonal. And I can imagine being under that and being on the other side of it. It has two sides that I can be on. One down here, and one up here. So that's just my first thing. You have a body. Imagine what it is to be under a sloping plane. You've been in them enough, probably, under a bridge. Like, it's one of the things that people struggle with planes is to imagine them going on forever as well. And so if you can make it big enough, it's easier to imagine that. But they're also not solid, right? They don't have a thickness, they're just like a piece of paper or a sheet. And so they have two sides. Okay. Don't know if that helps at all, but it's just something to point out. So here's a line. Lines in 3D can be in any direction. We're used to lines being down here on the plane. The line in 3D can slope in any direction you want, and they can come down and meet this plane down here at an angle. There's an angle here, but also there's an angle there, and an angle there too. But there's going to be a smallest angle for how it meets. And this is definitely not perpendicular to this plane. But this one is. And any line in any of these places will be perpendicular to this plane. And this line is parallel to the floor plane. And so is this one. And so is this one. They're all parallel to that plane. So it's feeling the options, because we feel like parallel should be like lined up with the walls, but it doesn't have to be. It just has to be the same direction plane. The line goes in every direction. This is perpendicular to this wall plane, and parallel to this means both. And most lines will meet both of these planes eventually. So, and I can't be parallel to both of these planes. Like I'm parallel to this plane, and I'm definitely going to be floor. So thinking about how many lines versus planes can be useful. Right, 2 lines. I have no idea if this is picking up on the microphone. It's on the screen. 2 lines in 3D space are capable of being parallel. These lines are pointing in the same direction. They are capable of meeting. Okay? And they are also capable of neither meeting nor being parallel. These 2 lines are called skew. They don't meet, and they're also not parallel. I can go along this line anywhere I want, and I'll never hit this one. Because the nearest point I come is where my hands are. And they're closer than that. But they're not parallel either. Tell me about what 2 parallel lines share. Correction? Cool. Anything else? Correction? They share a plane that goes through both of them. You can see where it is. Almost wide enough. I can put a sheet here that goes through both of those lines. Whereas these 2 lines, they're not planes for both at the same time. Put this one on the wall. I'm not there, I'm not. Let's look at the wall. There we go, see that there. Every plane through this line has to meet the wall. Because it already meets the wall. If it contains this line, it meets the wall purely. And every plane through any line in space, so all planes through this line here are like that. There's one there, there's one there, there's one there, there's one there, there's one there. There's a swing of planes that go through this line. And so if I imagine 2 skew lines, like this. Where is it? There. If I imagine 2 skew lines, every plane through this line is going to meet that line. Somewhere. The floor meets it here. But a perfectly vertical plane just here will meet it there, and a plane that goes that way will meet there. And so 2 skew lines have the property that every plane through one of them meets the other. Exactly 1 point. So, last but not least, a line can be completely inside a plane, or it can be exactly 1 point, like this, or it can be parallel to the plane, and miss it entirely. But again, there has to be a plane. If this is parallel to that plane down there, there must be a plane through it that's also parallel. 2 planes can be parallel as well. Just have another one that's a little higher up, or another one that's a little further along. Alright. So there's the walk of living inside 3D space and thinking of planes and stuff being there. That's that way of visualizing it, just to be able to think of those things. It's also good to be able to draw pictures that represent those ideas. So the pictures are that planes we tend to draw as pieces of paper or sheets. But we know that in our imagination they go on forever in every direction. But we don't want them to because we want to be able to see what's underneath them. And so I can imagine a plane and another plane, and they're parallel. Like that. And be parallel. Yep. And I can imagine a plane and a line going through it like that. Meeting 1 point. But it's good to be able to think of what it looks like when I'm down here, and what it looks like when I'm up here, and what it looks like when I'm standing on the line. How does it feel to be here in relation to these things? Like this is the floor, and the line that's coming up out of the floor, but it's also going down into the floor. Yeah. Okay. And the diagrams can be extremely difficult to draw. Yep. But the beauty of the mathematics is that it will work even if you can't imagine exactly where it is. If you just imagine the shape that plane is, it will be okay. And letting go, every representation loses something. No photograph shows every aspect of everything. Even at least 2 photographs to know what someone looks like because they have at least 2 sides. So it's the same thing. Every picture of anything, every representation of things loses something. What I've lost in my sheets and stuff is all of the coordinates. Yeah. So visualizing means you have to know what you've lost as well, but know whether it matters or not. So I know that there's only a few ways that a line and a plane can meet. And so I can imagine that I've got a generic picture of a line and a plane meeting. And I can say, well, this is what I got. I don't have to draw a graph of plane to know everything about it. But I'm going to do the graph that you said. I really shouldn't have chosen such big numbers. This plane, this is the equation of the plane. This technically is not the plane itself. This is just how to tell if a point is on the plane. And that's a useful thing to know. Like when you're visualizing, you also have to know a little bit how the math works. So this is an equation of a plane, which means it's a rule guiding if a point's on the plane or not. So you could imagine constructing this plane by picking a large number of random points and subbing them into this equation, and the ones that come out to 420 I'll colour in, and the ones that don't come out to 420 I won't colour in, and all the coloured ones are plane. That's what this is. And so I could draw that's 3D space. And what I'm imagining is this actually. There's an x-axis. No one's going to get to us if I draw a floor. X-axis here. And the y-axis here. And the z-axis there. And normally when I'm looking at it from here. See my x-axis, my y-axis sort of falls in front of me, my z-axis goes up. That's what this diagram here is saying. There's my x and my y is going. I'm imagining that there's a plane here like that the y-axis is in, and the z-axis is going upwards. Some people draw their axes in a different spot. If I stood in a different spot, if I stood standing here looking into this, then some people draw their axes like this, where this is x and this is y and this is z. That's a different view of the same thing. So this is very common in physics to draw it this way, and also in some math courses. But you can tend to draw it this way because I feel like this still looks like an xy plane, but just fallen down. So, okay. So if I want to draw a plane, I need 3 points. To draw a line, you only need 2. To draw a plane, you need 3. And I can figure out where it crosses the axes. So every point on the x-axis has 0 for both y and z. All these points line up with 0 on this axis and this axis. And so if I make y and z both 0, I get 6x is 420, and so x is 70. And if I want to be on the y-axis, then both x and z are 0, and so 5y is 420, and so 10y would be 840, so y would be 84. And if x and y are both 0, that puts you on the z-axis, which will be at minus 60 down there. So I've got a plane that goes through all 3 of those points, but it goes on forever, right? It goes on up here as well, and down there too, something like that. But a triangle is enough to know what direction it's in. It meets this xy plane in this line here. So I should have brought more than one stick, really, to be able to do this in the plane. No, that's right. If we were with more rectangular, it would be a little easier. I would draw things on the ceiling. Yeah. So I can't show you what's in my head. In my head, I'm standing here, underneath the xy plane, so that I can see that there's a plane above me. But if I stood here at the origin, the plane is below me. And so knowing where it is in relation to the other things, whether it's above or below different places, is a useful thing to know. Yeah. But it does come up here as well. Like if we follow those 2 lines, they'll all be part of the plane. So will this line here. Yeah. Oh, I've done it before. I like that. Like extending the triangles. That's fun. Okay. So cool. So most of the lines to the origin will hit this plane once. So if I've drawn down here, we'll hit it here. But some of them will be parallel to the plane. If I go in exactly the correct direction, they'll be parallel to the plane. And that direction is this direction, 5, 6, 6, 5, minus 7. Yeah. So 6, 5, minus 7. That direction there will hit the plane at a right angle. It's really cool. That magic trick is my favorite in Maths 1M. If I take these 3 coordinates, these are coefficients, and interpret them as coordinates, then that is the direction that is perpendicular to this plane. Yeah. And there's only one direction perpendicular to a plane. I mean 2 technically, one out here and one down there. And that's really cool. So if we live in 4-dimensional space, there'll be one direction perpendicular to a 3D thing. Like finding the equation of the plane is just the same as that line you and that whole time it's just one of those remember things. Okay, yeah, you know the plane, just actually drawing that and saying this is the coordinate, and now understand why that is how it actually works, and that's actually just a connection. So I don't know if this point here, that point there is definitely not this coordinate 6, 5, minus 7. Yeah. Yeah, you go cross product a couple of vectors, and that gives you a. I've never drawn this picture before, and I'm extremely happy about it. It literally just comes directly. It's like the height of this pyramid if I drew it this way, right? You come downwards. That's just so cool. I love it. I'm so glad that they helped you because it certainly helped me. Yeah. So some planes are parallel to one of the axes, and so you can't do that quite the same. And that tends to happen when one of them coordinates is 0. One of the coefficients is 0, and then it'll be parallel to one of the axes. Because this one's parallel to the x-axis of this plane without this, because this is normally a line in the yz plane, and any x coordinate is fine, and so it sort of extends outwards that way. Yeah. I should have brought little cubes. I do have some little metal cubes in the Maths Learning Centre specifically for this sort of drawing. Yeah, but I'm just put string on them to connect the pieces together so I can see where the plane is. So, yeah. And that's what we have an entrance to the Maths Learning Centre to be able to do things with the sheets. If you're new Mets, go to the Maths Learning Centre. The moment you're right at the beginning when you enter, there are axes on the floor. With blue for negative and yellow for positive. So people might have noticed it. It also has a handy place for lost souls together because, when tours come by, we've got a place to put them. But it's also there. It's a teaching tool. It's there to be able to walk graphs and that sort of thing. One thing I want to point out about these things is that everything is related, and so vectors are related to planes and lines in very fundamental ways. So if I'm on a line, whether it's in space or whether it's on paper, I can get to anywhere on this line by starting somewhere and going a multiple of any arrows I draw on that line. And so if this is v and this is p, then this point here is p plus v, where p has got coordinates as well. So you can imagine the origin somewhere, but it doesn't really matter. When you first learned addition of numbers that got you bigger than 10, you would say, 9 plus 3 is 9, 10, 11, 12. And so the thing you add acts differently than the thing that you start with. So addition is a starting place and a journey, and the answer is a finishing place. And this point here would be p plus 2 lots of v because I've gone twice that journey, and this point here would be p minus a half of v, and so on, right? So different choices for how many v's to add or subtract from this will produce every other point on the line. And so when you write something like this, what this is telling you is the coordinates of every point on this line. So what this is actually short for is
Every point on the line is some t. Every point on the line is reached by starting at this place and going some multiple of this journey. And so the journey this is the journey, so this is the start here. And this is the journey. This journey may longer or shorter by or changes direction by changing the value of t, still a journey. So the start plus journey equals final location. Yeah. And so in space, it doesn't matter what direction these things are. Just take this with me. Someone going to be upset me, because who else would need to do this? So I have point 103. There's 1 on the x-axis, 0 on the y-axis, 3 on the z-axis. We put 1, 2, 3 there, right there. That's obviously. And the vector 7 minus 7, 6. Well, 7 in the x direction, minus 7 in the y direction, 6 in the z direction. That's that vector. And so, right, not quite visible on the screen. So that arrow, I go in that direction as far as I want, or opposite direction. It produces a 1. Yeah, in space. Right. So it's really important to know the difference between what the two pieces of the equation are doing. First one, the beginning of the other journey. In fact, it's possible enough to be able to split it into. So that's why we're on that. You know when you've got point A and point B, and you've got the vector between them, which is the vector AB. Okay. Beginning plus journey equals end. So A plus the vector AB produces the point B. Therefore, the vector AB must be end minus beginning. Yay! That's my favorite thing. I don't think of it as an addition, but it's this calculation to figure out the vector from one place to another. Well, that's how you figure out a journey. You go to the end minus the beginning. That's the journey between them. And that's true for numbers as much as it is for vectors. 10 minus 3 is the journey from 3 to 10. 10 minus 13 is the journey from 13 to 10, because why it's negative, you have to go down to get from 15 to 10. Yeah, so cool, yay. So that visualization of vectors being journeys from one place to another is a useful way for me to visualize what's happening when I do these things. And so when you see vector proofs, they often, as much as I hate them, they often, it'll be like, all right, well, AB plus BD is the same journey as from A to D. So AD is the same as the journey from AB plus journey from B to D, produces the same journey. Yeah, and most of them are like that, and you can track around the thing as often as you want and get to the same spot. And as long as the journey goes from the same beginning to the same end, it's the same journey, and so you can do the thing. Yeah. Whereas if this is halfway, then you can say, well, AB is halfway A to C. Yeah, and so a lot of those things that are in vector proofs are directly based on describing in notation journeys in the diagram. Don't that helps at all. Yeah. So there's a classic problem I just want to do just because I know I'm going to do it now, but I just want to do it. Give me a second. Okay. Finding equations of the plane perpendicular to the line through 107 and 2 minus 35 and passing through 006. Yes. So the grammar of this sentence, we have the equation of the plane, and it's perpendicular to the line passing through 107 and 2 minus 35, and it passes through this point. That's the information about my plane. Okay. So, cool. So I'm going to imagine this. I don't really want to put them in specific spots on a set of axes. That's probably going to distract me from what's going on. What I'm seeing is that there are 2 points and there's a line through them, and my plane is supposed to be perpendicular to that, like that, and has to pass through this point 006. Cool, that's what it's asked. And I want the equation of this plane. There's often a follow-up question, which is where does this line meet this plane? Which would be here, which I don't know what that is. But that's my drawing of the situation, based on the idea that I have a line through 2 points. I know what that looks like. I can do 2 points. I know what a plane looks like when it's perpendicular to a line, and I know how there has to be a point in this plane somewhere. I don't know if this point is on this line or not, it doesn't really matter. And I can also imagine if I've got a line like that, and I've got a plane perpendicular to it, that could be the floor, or it could be here, 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 and 1 point will help me figure out exactly where that plane is. It's going to be how high up it is, or below the floor possibly, depending on where it is. So my imagining says that this should be possible because 1 point and being perpendicular to the line is, based on my experience of how planes feel in 3D, enough to figure it out. Cool. That's just the imagining of this thing. Totally not to scale or in the correct order. Right. Thoughts about how to track this? Yep, trying to figure out what this line is. Cool. That's going to happen at some point, so I might as well do it now. So it seems to me that if I could figure out any arrow on this line, then that would be allowing me to do that move I did before, where all the points on the line are location plus multiple of arrow. And so this journey should be the one I want. I'm going to call these by names so that I can do my calculations a little easier. The vector from A to B, not that it matters which way it is, would be B minus A. So 2 minus 1 is 1, minus 3 minus 0 is 2, minus 3, 5 minus 7 is minus 2. That's the vector from AB. And so every point on this line will be some multiple of AB away from that point there. Or this point doesn't really matter, but I'm just laid on the pie diagram. It strongly suggests that all the points on the line are equal to the starting point A plus some multiple of the journey from A to B. So t is the number between 0 and 1, it'll be just a percentage of the journey from A to B, it'll be partway between A and B. If t is more than 1, it'll be on this side. If t is less than 1, it'll be on this side. Less than 0, sorry. If t is negative, it'll be on the other way. If t is between 0 and 1, I'll be in here. If t is more than 1, I'll be over here. So this comes back in Math 1A actually, that the way to make the space, the journey, the line segment from A to B is to do this over t less than 1. So very cool. Okay, so these are all the points on the line. So this vector is in the same direction that this line goes, which means this vector must be perpendicular to this plane. So that means that this vector must be a normal vector for this plane. Which means that the plane must have an equation like 1x minus 3y plus 2z equals something, for some number. I should call it b because I don't have A, B, and C in these spots. And if I put A here, I'll just figure myself out because it's in the spot. Cool. So even if I couldn't finish my problem, at least I've still got an equation that's possible. Now I just have to decide what the correct d is to make it go through this point. And the information I have about how plane equations work is that if a point is on the plane, this equation will be true. And if a point is not on the plane, this equation will not be true. And so since this point is on the plane, subbing this into here will be true. So sub in 0, 0, 6. And then 0 minus 3 times 0 plus 2 times 6 must be d. Because all the points on the plane produce d when you put it into the equation. And so d is 12, and so therefore the equation is x minus 3y plus 2z is minus d is, no, d is plus 12, I'm all good, is 12. All the points on this line, on this plane, satisfy that equation. What I'm going to say is that this diagram helped me to keep my information together in a way that was easier for me to see. I didn't have to go and read the original question again, see what the information told me, because the picture told me that this point is on the plane. Yeah. Okay, I don't need it to be in the right place because I know there's only a small number of options for how planes and lines can be arranged. And yeah, and back here in this diagram, this was lovely, but if I was standing in the right spot, it would be just the floor and the vertical line. And so imagine knowing that you can stand in the right place to make it look the way you want is a really useful thing to know. I'm glad that was useful for you. And so that not to scaleness is a skill that has to be learned separately for each particular kind of thing. Yeah. Yeah, the picture holds the information in a way that the sentences are hard to get it out of. So like I said that before, that the pictures help organize your information, even if they don't do anything other than that. Yeah. So for some people, this picture would be helpful. It would call them to take these sentences and write a little table of information. Yeah. So if I wanted to find where this line met this plane, that would be this here. I know that all the points on this line are that plus some of this vector. And I know that all the points on the plane satisfy this equation. So I need a point that satisfies that equation and also is made by doing LFT of AD. So they didn't ask me to do this, but that's a classic problem that people struggle with. There are two ways to tell someone about an object like a plane or a line. One way is to tell you all the points on the object are, and one way is to give you an equation to sub things into to see if it works or not. And I have one of each. I have that all the points on the line look like this, and I have that all the points in the plane satisfy this equation. So if I want something that's both on the line and in the plane, it has to do both. So the point is on the line, so it is 107 plus t, 1 minus 3 minus 2 for some value of t, which I don't know what it is yet. Going to leave some space to do some working. Point is on the plane, so its coordinates satisfy x minus 3y plus 2z equals 12. And since it's both on the line and on the plane, it has to do both. So this will tell me what its coordinates are, and I can sub them into there and it should tell me what t is. So I've got 1 plus t, 0 minus 3t, 7 minus 2t. And so I've got that 1 plus t minus 3 lots of minus 3t plus 2 lots of 7 minus 2t is supposed to be 12. And that should tell me what t is if I'm careful. (10t minus 4t is 6t, 12 minus 14 would be negative 2, minus 1 would be negative 3, and so t is in fact minus a half. I had the algebra right there. I wasn't paying attention just a second. 9, 14 plus minus 14. 1 plus 9 is 10 minus 4 is 6. 12 minus 14 is negative 2, minus another minus negative 3. So about 6 is a half. Yep. And so therefore, the point is this point, right? Where t is actually minus a half, so I can put that back into the formula. Damn it. A half, 3 halves, 7 plus 2 is 9. But just from a visualization point of view, it says that my diagram, the plane's actually on the wrong side. What it says is that here's the point A, here's the point B, right? And here's the vector AB. So t is minus a half, which means it's actually here. And so the plane I'm interested in is actually over here. Yeah. They didn't matter to do the picture. Because the picture had all the information I just tried to need, even if it was in the wrong order. That's one of the big ideas in geometry is that it doesn't really matter what, sometimes it doesn't really matter what order things are in, because the algebra works out the same anyway. Yeah. Now that could be because I studied projective geometry where there is no such thing as order or angle. So I'm used to just putting things wrong. But yeah, that's what actually happened, because that's minus a half AB here. So I've gone the wrong way only halfway. So 0.100, whatever is up here somewhere. Yeah. So they don't match, but it doesn't matter, it works out fine. So some of the reasoning is not about, now I did entirely reasoning without thinking of any pictures whatsoever, because it was about the algebra that tells me whether a point is on the line of the plane at the same time. Yeah. I always say things are my favorite bit, but my favorite bits of a math course are the bits that I understand. I really don't like parts of a math course that I feel like I just have to do understanding, they make me feel uncomfortable. And it's one of the reasons why in second year when I was at uni, I didn't do differential equations, because I just didn't feel like I understood what the hell was going on. I get it, I could integrate both parts and whatever, but the stuff in Maths 1B I did. But now that I'm at this end and have understood some of it because I had to teach it, There are more favourite bits for me. I understand them. Yeah. Well, that's enough of that. I'm going to stop there.